Now let's take a look at Mount St. Helens specifically. Here we have lava flows. Lava flows from Mount St. Helens typically affect areas within 6 miles, 10 kilometers, of the vent. However, two basalt flows erupted about 1,700 years ago, extended about 10 miles or 16 kilometers from the summit. One of them contains the Ape Cave lava tube. That's how it formed. Lava flows typically follow stream drainages and spread out in areas of low relief. Few people live in areas subject to lava flows, but lava flows originating from Mount St. Helens could start forest fires and destroy roads and bridges. Lava flows that encounter snow and ice could cause melting and generate lahars. A lahar is also called a volcanic mud flow or debris flow, a mixture of water and volcanic debris that moves rapidly downstream. I wasn't done with you yet. Come back. Consistency can range from that of muddy dishwater to that of wet cement, depending on the ratio of water to debris. So if you get mud with the volcanic material from the lava, that's a lahar. Now the lava dome. Viscous lava, remember Mount St. Helens is high water, high silica. And if you haven't read the lava types, go to that one. May pile up over vents to form steep-sided lava domes, like that big old dome there is an example, or thick, stubby lava flows. If you read how composite volcanoes are formed, it's lava flows mixed with ash and cinders from explosive eruptions. So it's a combination of a cinder cone and a shield volcano. On steep slopes such as the volcano's upper flanks, the parts of these lava masses may collapse, spawning avalanches of hot volcanic debris, block and ash flows that generate pyroclastic flows and surges. So pyroclastic is a hot, typically over 800 degrees Celsius, mixture of rock fragments, gas, and ash that travels rapidly away from the volcanic vent. So what makes a pyroclastic flow different from a mud flow, it's that it's got hot lava as part of it, whereas the mud flow is not as hot. Hence the word pyro, meaning fire, and clastic, meaning rock. Dome building can go on episodically, it doesn't happen continuously, for decades to centuries. And the dome growth episodes in 1980 to 1986 and 2004 to 2008 will likely be followed by others. As the lava dome grows surrounded by crater glacier, there is an increased probability that lava dome collapse may occur, swiftly melting snow and ice and generating more lahars. If past trends are repeated, now here's where scientists are making an inference based on the observation from the past. Renewed dome growth may be preceded by a few days to weeks of heightened seismicity, and that means earthquakes. Ground deformation, the surface of the ground is going to change shape because the magma's coming up as lava, and gas emissions, so more gas is going to escape through that dome. Small to moderate explosions often herald the start of new eruptive activity. So as more stuff explodes in there, as it builds, it's going to cause more eruptions, and that's why they happened from 1980 to 1986, and again in 2004 to 2008. So this has a little bit of information to help you write the first raft, being the volcanologist. Let's take a look at the ash tephra fall. Mount St. Helens produces small to large explosive eruptions, which send varying quantities of ash and tephra into the atmosphere. And there's a picture of an ash cloud of the eruption from 1980 over Ephrata, Washington. That cloud is ash. Tephra is defined as any type and size of rock fragment that is forcibly ejected from the volcano and travels airborne during an eruption. So that's the definition of tephra. The May 18, 1980 tephra plume, is what they call that big ash cloud, lasted for about 8 hours. Other sources say 9. And the plume top ranged from 14 to 18 kilometers. That's 8.5 to 11 miles into the sky. Ash fallout caused major problems in communities up to 600 kilometers, that's 370 miles, away. The major hazards, so if you're writing as the governor, here's some hazards that more research into volcanism can help solve. The major hazards associated with eruption of tephra result from suspension of the abrasive fine particles in the air and water. Now these particles, the ash, the cinders, the tephra, can bury transportation routes and vegetation. Talk about all our food, including our trees. They load on roofs or other structures. Okay, so these are hazards they can cause. Volcanic ash may pose hazards hundreds of kilometers downwind from the source, directly after accumulating at the surface and later when particles are remobilized by wind or passing vehicles. So airplanes, forget it, they can't fly during this thing. And cars, their air filters are going to get clogged up and it causes a huge mess. Airborne ash causes eye and respiratory irritation, damages unprotected machinery, especially internal combustion engines, tractors, cars, trucks, you name it, and often causes short circuits in electric power transmission and distribution lines. It endangers aircraft, which may completely lose engine power if they fly through ash clouds. Ash particles further act as contaminants in water supplies, leading to damage at hydroelectric facilities, irrigation pumping stations, sewage treatment facilities, and stormwater systems. There you have a bunch of text-based evidence to make your case to Congress. But there's more. Ballistic projectiles. That is bigger pieces of rock shooting out of a volcano like a bomb. Volcanic explosions can propel rock fragments on ballistic trajectories that may differ from the wind direction. These events may occur without warning and in the absence of a larger magmatic eruption. Magmatic is a fancy word for magma coming out. A blast related to the emplacement of the Sugar Bowl Dome, that's what they named part of the dome, on the north flank of Mount St. Helens about 1,200 years ago, propelled ballistic fragments as large as 5 centimeters, 2 inches, as far as 10 kilometers or 6 miles from the vent. That's a 2-inch piece of rock flying 6 miles through the air. Think of how much force it took to propel that thing. More typically, ballistic projectiles are limited to within 3 miles of vents. Let's take a look at the pyroclastic flows, because man, that's where you're talking about a lot of trouble. And by the way, if you're writing as Mount St. Helens, this is all part of your eruption. Releasing all that pressure, releasing all that ash, cinder, tephra, bombs, ballistic projectiles. You're getting rid of all that. Not to mention the whole side of your body crumbling down and flowing away and then getting blown up. So during historical eruptions of Mount St. Helens, pyroclastic flows, the hot ones, have originated from collapsing eruption columns and from gravitational or explosive disruption of growing lava domes. So gravitational, gravity is pulling things towards the center of the Earth, so it helps bring anything that shoots upward back down. So driven by gravity, pyroclastic flows seek topographically low areas. In other words, it's flowing downward and can travel down valleys, into rivers, into Spirit Lake and the Toutle River. That's how it happened. And can travel down valleys at high velocities beyond the flanks of the volcano. They pose lethal hazard from incineration. In other words, you will burn to death. Asphyxiation, you can't breathe that stuff, you will die. Burial, like Harry Truman, he got buried. And impact, you get hit by that, you're dead. They are difficult or impossible to escape. Therefore, evacuation of likely hazardous areas must take place before such events occur. You have better prediction of when it's going to erupt. You can evacuate people and save more lives. Governor Raft. Pyroclastic flows from the May 18, 1980 eruption ran out no farther than 8 kilometers, 5 miles from the vent. During the past 4,000 years, numerous pyroclastic flows are known to have traveled at least as far as 10 to 15 kilometers, which is 6 to 9 miles. And one older flow reached 20 kilometers, 12 miles from the source. The present orientation of the volcano, with the open crater to the north, favors distribution of pyroclastic flows into the North Fork Toutle River Valley. However, all flanks of the volcano are subject to pyroclastic flow hazard during a large explosive eruption. Now if you click here, where it says hazards, it takes you to this page with a great picture. This picture here shows the Mount St. Helens hazards map, showing potential impact area for the ground-based hazards. The pink is near the volcano, lava and pyroclastic flows, thick tephra, lahars, ballistic ejecta, which is the bombs flowing out of it, and the rockfall. Where it's red and orange, those are the lahars, the volcanic mud flows. And then this side, where it's this beige color, the regional lava flows from the vents, and they're dispersed between major volcanoes. What they don't show here is the volcanic ash, which goes with the wind, wherever the wind blows. Let's take a look more at lahars. Mount St. Helens is susceptible to lahars because the vent and the site of recent lava dome building is surrounded by crater glacier. Furthermore, the crater floor and flanks of the volcano are made up of the large amounts of loose volcanic material and are covered with a thick snowpack for much of the year. You mix all that loose cinder and dried up lava flow with melted ice, you're getting a huge mud flow, which is a lahar. Lahars generated by rapid snowmelt are likely to accompany an eruptive activity. That means when a volcano erupts, the snow melts, you've got all this hot lava, and it's going to make a lahar and a pyroclastic mud flow. But they may also be generated without an eruption by intense storm runoff over the erodible sediment or by landslides. So it doesn't have to happen during an eruption. Here's a picture of a lahar originating from Mount St. Helens after the 1980 eruption. It destroyed more than 200 homes for over 185 miles of road. Here's the picture I showed in class, the one I have on the Tripbook webpage. Lahars causing that mudline riverside trees to just be taken with the mud. Past lahars at Mount St. Helens have traveled from 50 to 100 kilometers, that's 30 to 60 miles, from the source, often reaching the Columbia River via the Toutle, Cowlitz, the Kalama, and Lewis rivers. They are a greater threat to life and property in valley communities than any other volcanic phenomenon. There's more info for the governor. Damage is done by impact from large boulders or logs carried in the flows, by high drag and buoyancy forces imposed by the dense fluid, by abrasion, and by burial. Lahars commonly destroy mature forests and any human-made structure in their paths, including bridges, roads, pipelines, and buildings. In the event of a lahar, and with enough warning, people can quickly climb or drive to safety by evacuating the valley floor. So you gotta have early warning. During the May 18, 1980 eruption of Mount St. Helens, approximately 2.3 billion cubic meters, that's 3 billion cubic yards of material was deposited in the upper 27 kilometers or 17 miles of the North Fork Toutle River Valley, resulting in massive lahars. Now click up here where it says Geology and History, and there you have a great picture showing the lava dome, how big the summit was before the eruption. What's called the pumice plain, the landslide deposit, and Spirit Lake. Now remember, we were here, and we were looking at it this way. And Windy Ridge is right about there, so we were right about there, looking into that dome. So we were looking at the Sugar Bowl. We could probably see the Lewitt Falls. And sometimes I've had cameras that could look up closely and see the waterfall over there. But the lava dome is in here. The 1980 is right there, the yellow. There's Crater Glacier, and that's where we even saw some ice there, if you look at the pictures I took. But here's for, if you are Mount St. Helens, go here to May 18, 1980. If you're writing an email to Mount Rainier, here's where you're going to be able to explain scientifically about your eruption. There's a lot to read here, and it goes over the Lahars, Plinian eruption. All right, let's get to some of this. I'm going to jump down here to the debris avalanche, the lateral blast, and the Plinian eruption, because those are the big ones. Debris avalanche. With no immediate precursors, a magnitude 5.1 earthquake occurred at 8:32 a.m. on May 18, 1980, and was accompanied by a rapid series of events. At the same time as the earthquake, the volcano's northern bulge and summit slid away as a huge landslide, the largest debris avalanche on Earth in recorded history. A small, dark, ash-rich eruption plume rose directly from the base of the debris avalanche scarp, and another from the summit crater rose about 200 meters, or 650 feet high. The debris avalanche swept around and up ridges to the north, but most of it turned westward as far as 23 kilometers, or 14 miles, down the valley of the North Fork Toutle River, and formed a hummocky deposit. The total avalanche volume is about 3.3 billion cubic yards, equivalent to 1 million Olympic swimming pools. And there is the bulge. So if you're writing as Mount St. Helens, you're a mountain sitting there, and your side just bulges and collapses down. So you're describing that. The lateral blast. Oh, okay, here we go. The landslide removed Mount St. Helens's northern flank, including part of the cryptodome that had grown inside the volcano. The cryptodome was a very hot and highly pressurized body of magma. See, it's this pressure that was building in there and caused it to break through. Its removal resulted in immediate depressurization of the volcano's magmatic system and triggered powerful eruptions that blasted laterally through the sliding debris and removed the upper 300 meters, nearly 1,000 feet of the cone. Whoa. That fancy sentence is saying that as the pressure got released by the north side of the mountain sliding, magma triggered powerful eruptions, and that eruption is what blew sideways. That's what it means by blasted laterally through the sliding debris. As it's sliding down, the pressure went sideways because it had a way out and removed nearly 1,000 feet of the cone or the summit of Mount St. Helens, of you, if you're writing this as Mount St. Helens. As this lateral blast of hot material overtook the debris avalanche, it accelerated at least 480 kilometers per hour. That's 300 miles per hour. Within a few minutes after onset, an eruption cloud of blast tephra, that's that hot rock fragment ash, began to rise from the former summit crater. See, now there was a huge gaping hole there, and all this ash started shooting up. Within less than 15 minutes, it had reached a height of more than 15 miles, or 80,000 feet. The lateral blast devastated an area nearly 30 kilometers, or 19 miles, from west to east, and more than 20 kilometers, 12.5 miles, northward from the former summit. In an inner zone extending nearly 10 kilometers, or 6 miles, from the summit, virtually no trees remained of what was once dense forest. Just beyond this area, all standing trees were blown to the ground, and at the blast's outer limit, the remaining trees were thoroughly seared. The 230 square mile devastated area was blanketed by a deposit of hot debris carried by the blast. Now this is the Plinian eruption right there. That's what a Plinian eruption looks like. Plinian eruption. Removal of the cryptodome and flank exposed the conduit of Mount St. Helens, resulting in a release of pressure on the top of the volcano's plumbing system. That's what went up. This caused a depressurization wave to propagate down the conduit to the volcano's magma storage region, or what's known as the magma chamber. We read that in the book, the textbook. Allowing the pent-up magma to expand upward toward the vent opening. So imagine this magma is going up towards the vent opening because it now has a way out because of the pressure. Less than an hour after the start of the eruption, this loss of conduit pressure initiated a Plinian eruption that sent a massive tephra plume high into the atmosphere. Beginning just after noon, swift pyroclastic flows poured out of the crater at 80 to 130 kilometers per hour. That's 50 to 80 miles per hour, and spread as far as 8 kilometers or 5 miles to the north, creating the pumice plain. And we know what pumice is. The Plinian phase continued for 9 hours, producing a high eruption column, numerous pyroclastic flows, and ashfall downwind of the eruption. Scientists estimate that the eruption reached its peak between 3 and 5 p.m. When the Plinian phase was over. A new northward opening summit amphitheater, 1.9 by 2.9 kilometers, about 1.2 to 1.8 miles across, was revealed. Ooh, here's a picture of the ash cloud over Ephrata, Washington again. These people are looking up. I mean, go to the webpage if you can't see this on the video. Over the course of the day, prevailing winds blew 520 million tons of ash eastward across the United States and caused complete darkness in Spokane, Washington, 250 miles from the volcano. Major ash falls occurred as far away as central Montana, and ash fell visibly as far eastward as the Great Plains of the central United States, more than 930 miles away. The ash cloud spread across the U.S. and in 3 days circled the Earth in 15 days. Okay, that's odd. The ash cloud spread across the U.S. and in 3 days circled the Earth in 15 days. That's a weird sentence. So maybe it took 3 days to circle the Earth, but then what did it take 15 days? Okay, that one's confusing. So now you have enough information to write incredible rafts. Go for it.